Welcome to This Explainer. Right off the bat, I want you to take a quick look at the device you might be holding in your hand right now. I mean, whether it's a smartphone, a tablet, or the monitor you're sitting in front of, we literally spend hours staring at these things every single day, right? But let's look past the slick user interface for a second. We're going to dig into the actual physical chemistry firing off just beneath that glass. So what exactly is making your screen glow right now? It's kind of fascinating when you think about it. We completely take for granted those incredibly vibrant reds, the deep greens, and the crisp whites that bring all our photos and videos to life. But here's the thing. Those crisp colors aren't just digital magic. They are the result of highly specific rare earth chemistry happening, literally, millions of times a second. Today, we're unpacking the secret ingredients responsible for those stunning visuals sitting right there in your pocket.
Which brings us to part one, the metals in your pocket.
Now, you probably already know the structural heavy hitters in your electronics. You've got copper handling the high-speed conductivity, aluminum managing the heat so your phone doesn't melt in your hands, gold preventing corrosion at those microscopic contact points, and of course, lithium powering the whole shebang. But while these metals give the device its pulse and structure, they don't give it its vibrant visual life. For that, we actually need to look somewhere else. To get that visual pop, engineers turn to rare earth metals. This is a very specific group of 17 chemical elements with completely unique optical, magnetic, and electrical properties. And here's the crazy part. They are deployed in incredibly microscopic amounts, but their specific electron configurations make them absolutely irreplaceable for modern displays. You literally just cannot replicate what they do with any other materials. It's a one-of-a-kind chemical footprint.
Moving right along to part two, rare earths in your screen.
Okay, let's zoom in a bit. Inside your screen, specific rare earths act as phosphors, with a very strict division of labor. It's almost like a tiny factory in there. Europium, that one is exclusively responsible for emitting bright red light. Terbium handles those vivid greens. And yttrium acts as this stable host lattice, basically the foundation, for these phosphors to actually operate. So when you're looking at a beautiful, high-definition sunset on your phone screen, you are actually seeing the highly specific optical properties of europium and terbium doing their thing.
Just imagine trying to paint a masterpiece, but someone came along and took away your primary colors. That's what it'd be like. Without europium, terbium, and yttrium, we wouldn't just lose our color accuracy, screen efficiency would completely plummet, and modern batteries would drain in a fraction of the time. The high-definition, energy-efficient screens we literally rely on every single day just wouldn't exist without this specific trio.
Let's get into the mechanics of it in part 3, the science of screen glow.
The physics here is all based on a really cool concept called electroluminescence. Here's how it works in 3 simple steps. First, an electrical current from your phone's battery is introduced into the semiconductor material. Second, this current causes charge carrier electrons inside the material to get highly excited, but, they can't stay hyped up forever. Step 3 is where the magic really happens. As those electrons relax and return to their normal state, they have to release that excess energy. In these highly specialized rare earth phosphors, instead of releasing the energy as boring old heat, they emit it as visible light.
And honestly, the level of control here is mind-blowing. By carefully tweaking the exact mixture of those rare earth elements and precisely controlling the electrical current, engineers can perfectly manipulate the emitted light. This is exactly how your screen can instantly switch from displaying a stark white web page to a dark, moody movie scene with absolute pixel-perfect accuracy. It is literally chemistry and physics working together at the speed of light.
But of course, there is a catch. Section 4, the hidden environmental cost.
Think about this staggering number for a second. 530 pounds. According to research from the United Nations University, it takes over 530 pounds of fossil fuels, along with 3,300 pounds of water and 50 pounds of chemicals just to manufacture a single 53-pound computer and monitor setup. To put that crazy ratio into perspective, when you manufacture a car or a refrigerator, the weight of the fossil fuels used is roughly equal to the weight of the product itself. But for electronics, you're using 10 times the product's weight in fossil fuels. The contrast between our tiny, sleek devices and the massive footprint required to extract their internal materials is, well, it's pretty eye-opening. And because extracting these specific elements is so incredibly complex, production is highly concentrated in just a few global regions. The tech industry basically relies on a razor-thin supply chain. So if there are geopolitical or logistical disruptions in those specific areas, it instantly hits device availability and, you guessed it, pricing.
So where do we go from here? Part 5,
The future of smart displays.
Our demand for these materials is only accelerating. I mean, we all want thinner devices, higher resolution color, and batteries that actually last all day, right? But every single step toward miniaturization or higher efficiency directly drives up the volume of rare earth metals required by the industry. Our collective appetite for better, brighter tech is directly driving up the need for these obscure metals.
But here is where the solution comes into play. Proper electronics recycling is absolutely vital. When we recycle, we aren't just saving structural metals like copper, we are actively recovering that precious europium and terbium. It's basically urban mining. Recycling keeps these elements in circulation, which directly reduces the massive environmental toll of having to extract brand new materials from the earth just to build the next generation of smartphones.
Which leaves us with a pretty huge, crucial thought to ponder today. As our technology advances and our screens get brighter, sharper, and more brilliant, can we ensure our supply chains actually get greener? The microscopic chemistry inside your screen is an absolute marvel, for sure, but understanding its journey from the mine to the phosphor is what will truly define the future of consumer tech. Thank you so much for joining me for this explainer. The next time you look at a vivid red or green on your phone, you'll know exactly what kind of microscopic magic made it happen.